Atomic structure 3, electron configuration and orbitals and electron configurations. The electron configuration of an atom can be deduced from its atomic number. Again, we're looking at how theories are superseded, and as before, it's worth thinking about Heisenberg's uncertainty principle with regards to our actual knowledge of electrons. The Bohr model and electrons. What rules have you been using when assigning electrons to energy levels? Well, firstly, we know that the number of electrons in a neutral atom equals the number of protons. Also, we've been told that maximum number of electrons per energy level are as follows. In the first energy level, there's 2 electrons. In the second energy level, 8. The third energy level, 8. And the fourth, 8. Well, I can tell you that the number of electrons in a neutral atom does indeed equal the number of protons, and that in the first and second energy levels there are 2 and 8. However, in the third and fourth there are not 8. There are in fact 2n squared number of electrons. So in the third energy level it'll be 3 squared. 9 multiplied by 2 gives us 18. And next, 4 squared times 2 is 32. 16 times 2. The 2 models for the hydrogen atom below describe the path and position of electrons differently. The Bohr model shows that electrons occupy defined energy levels, a little bit like a solar system with planets going around the sun. Instead, it's electrons going around a positive nucleus. Electrons have a fixed distance from the nucleus, and electrons travel in a predictable path. In the quantum mechanical model, energy levels above the first energy level have energy sub-levels. Within each sub-level, electrons occupy orbitals, regions of space with a high probability of finding an electron. And orbitals do not have a fixed space. Electrons move randomly within these orbitals. So, the sublevels. Each energy level above the first energy level contains energy sublevels. You can see here the first energy level only has 1 energy level, sublevel, sorry. And the second energy level has 1, 2. The third has 1, 2, 3. And the fourth has 1, 2, 3, 4. These sublevels are designated as S, P, D, and F. There are others. These sublevels. The sublevels within an energy level have very similar energy values. So let's look how they divide. You've got low energy at the bottom here, and you've got high energy up top there. In the first energy level, second energy level, third energy level, you have 1 in the ground energy level. In the second energy level, you can see it's divided into 2 sub-levels. And the third one is divided into 3 sublevels. It's kind of easy to remember how many sublevels are in each energy level because they match. So in the fourth energy level, there's 4 sublevels. Easy, right? Sublevels are identified as S, P, D, or F. And the energy of sublevels slightly increases as we go from S to P to D to F. In the first sublevel, we have 1s. Oops. In the second sublevel, we have 2s and 2p. 2 stands for second sublevel, and the letter is for the type of sublevel. Third sublevel, third energy level, which has 3 sublevels, and that's 3s, 3p, and 3d. And the fourth energy level has 4 sublevels, 4s, 4p, 4d, and 4f. Okay, let's look at orbitals. An orbital is just a region of high probability of finding an electron. An And orbitals can only hold 2 electrons. Each type of sublevel has different orbitals. Let's have a look. The first one we'll look at is the s orbital. And you can see it's a spherical shaped orbital. And there's only one type. The s sublevel holds a maximum of 2 electrons, and because there's only one orbital, then it can hold 2 electrons. The p orbitals, they are dumbbell shaped, or some people call them figure of 8 shaped orbitals. There's 3 types, and the p sublevel holds a maximum of 6 electrons. There's 3 orbitals, each holds 2 electrons each, so 6 electrons. The d orbitals, you can see there's 5 there in different shapes again. There's a kind of clover-leaf shape, a 4-leaf clover, and there's a torus there in the middle. And there's 5 orbitals. The d sublevel holds a maximum of 10 electrons. There's 5 orbitals, each holding 2, so 10 electrons. Finally, we have the f orbitals. And there's many shapes here. 7 of them. And because there's 7 orbitals, each holding 2 electrons, then altogether f can hold 14 electrons. Let's fill in this table, shall we? So, for the first energy level, number of sublevels is 1. Type of sublevels, s. Sublevel designation, obviously be 1s. Number of orbitals, there's just the s. And the maximum number of electrons it can hold is 2. Second energy level has 2 sublevels. There's s and p type orbitals. Second energy level, and s and p, 2s, 2p. Number of orbitals, the p, there's 3 types. S, there's 1 type, so 4 altogether. And because there's 4, and each can hold 2, it can hold a maximum of 8 electrons. And the third energy level has 3 sublevels, S, P, and D. So we have 3s, 3p, and 3d. S can hold 1, there's 1 type of S, there's 3 p orbitals, and there's 5 d orbitals. So altogether 9 orbitals, each holding 2 electrons, so a maximum of 18 electrons. And finally, in the 4th energy level, there's 4 sublevels, S, P, D, and F. The sublevel designation, 4s, 4p, 4d, 4f. I think you're getting the hang of it now. The number of orbitals, there's 1 s, there's 3 p orbitals, 5 d orbitals, and 7 f orbitals, so 16 altogether. And yes, you're right, that means it can hold 32 electrons. And this fits the formula 2n squared. So have a go at these. Press pause and complete the questions. Press pause. Really press pause. Press it now and don't start again until you have completed them all. Okay. Have a look. Did you get them all correct? If so, do the dance of joy. If not, go back, have a look at the video again and try and improve your understanding. Okay, electron arrangement versus electron configuration. Nitrogen here has an atomic number of 7. Remember, Z is the atomic number. The electron arrangement is 2, 5. It's got 2 in the first energy level. It's got 5 in the next energy level. The electron configuration is 1s2. It's got 2 electrons in the s shell, and then it's got 2 electrons in the second s orbital, and 3 electrons in the 2p orbitals. Let's look at some simplified rules for arranging electrons into sublevels. The number of electrons per sublevel is calculated using the Pauli exclusion principle. Each orbital has a maximum of 2 electrons. S, there's 1 orbital, so it has 2 electrons. P has 3 orbitals, so there's 6. The D has 5 orbitals, so there's 10. The S, the F has 7 orbitals, and so there are 14 electrons. Simplified rules for arranging electrons into sublevels. Secondly, we use the Aufbau principle. Electrons fill sublevels from the lowest energy level upwards. This gives the lowest possible potential energy for electrons in atoms. And you can see as we go up here, there's an increasing energy. Carbon has 6 electrons, and so it'll be 1s, 2, 2s, and 2 electrons in there, and then 2p, and there would be 2 electrons there, 2, 4, 6 electrons. Sulfur has 16, so it'll be 2 electrons in 1s, 2 electrons in 2s, 6 electrons in 2p, 2 electrons in 3s, and 4 electrons in 3p. The order of filling is more complicated after 3p is filled. The sublevels in higher energy levels start to overlap, as do their energy values. Let's have a look at this. I'm just going to draw out all the levels and the sublevels. You can see I've included these ones here, which you needn't worry about. This is just where electrons can go when excited, when they're in an excited state. So how do we fill these orbitals? It's like so. 1s first, then 2s, then 2p, 3s, then 3p, and then look, it's gone to 4s. It didn't go to 3d first. Then 3d, 4p, 5s, then 4d, 5p, 6s, 4f, 5d, 6p, 7s, etc. So you can see there's a pattern which can be easily drawn out if you were doing a test, for example, and you wanted to remember what the order is. Okay, calcium has 20 electrons. So let's fill it up. 2 in 1s, 2 in 2s, 6 in 2p, 2 in 3s, 6 in 3p, and then look what's happened. From 3p, it's gone to 4s. It did not go to 3d, 2 and 4s. For titanium with 22 electrons, I'm just going to catch up to the bit. Yeah, okay, so we've got 3p6, and then next we know it's the 4s instead of the 3d, and then 3d is filled. So 3p, then 4s, then we go to the 3d. So following the arrow. And the 3d has 2 electrons. Oops. Okay, can you please deduce the electron configurations for the following? Press pause, have a go. Pause. Press pause and do it. Good. Okay. Check that you got them right, and well done if you did. If you didn't, why don't you skip back, have a look at the previous few slides, and then have another go. Okay, transition metals. Some don't follow the order of filling. Well, that's great news, isn't it? For example, chromium. The valence electrons here, 4s2 and 3d4, you'd expect there to be 2 electrons in the S and 4 in the D. This is what we predict from what we've just learned. However, this is actually what occurs. You have 1 electron in the 4s and 5 in the 3D. So what's going on? Well, when all d orbitals are half filled, the atom is more stable. And so one of these electrons prefers to go into the d orbital, because this is energetically more favorable. It is more stable. Copper, 29 electrons, and so the valence electrons are drawn here. We'd have, or we predict to have 2 electrons in 4s and 9 in 3d. However, once again, we get an electron skipping along to fill the 3d, leaving the 4s with one electron. When all d orbitals are filled, the atom is more stable, and that's why it happens. This change happens when electron configuration ends with 4d, with d4 or d9, sorry. So make sure you're looking out for that. And don't you worry about this either, these square bracket things. I will tell you all about that in a bit. Okay, when removing electrons, what happens? When removing electrons from transition metal ions, let's have a look. Nickel first. So the valence electrons here, we've got 4s2 and 3d8. What would we expect to happen? Well, I guess we'd expect, since this seems to be the outermost orbitals, that we're going to lose 2 electrons from the 3d sublevel to get this. But that isn't what happens. And it's a very common error that people make. So make a note of this and don't forget it. When positive ions form, electrons must be removed from the outermost energy level. That would be 4s. And so 4s loses 2 electrons, and this would be the electron configuration for the nickel cation 2+. You can see we've got 3p6, 3d8, and no 4s2, no electrons in the 4s orbital. Okay. Press pause again and have a go at this. Write the abbreviated electron configuration for iron 2+ and iron 3+. Okay, well, iron is a neutral atom with 26 electrons. And so the valence electrons are 4s2 and 3d6. When it loses 2 electrons, obviously, because we just learned this, it's going to lose the 4s2 to just get 3d6. And this is why the Fe3+ is quite stable, because when it loses another electron, when iron loses 3 electrons, you get 3d5, half filled d sublevel, which is stable. There's no electron pairs repelling each other. Now don't, again, worry too much about this here. It doesn't stand for abbreviated, by the way. Okay. The periodic table follows the Aufbau order of filling. As atomic number increases, let's have a look. Got the S block, the P block, the D block, and the F block down at the bottom there. Let's say if we look at the 4s, or if we look at the 4th period, 4s fills first, then 3d, then 4p. So what was that abbreviated business that we looked at before? We had the square brackets, and the examples previously had AR. What was that all about? Well, let me tell you. In row 1, we've got row 1, row 2, row 3, row 4. You can see that the elements in row 2 all have the electron configuration of helium and then some valence electrons. You see? Then, if we look at row 3, they all have the same electron configuration as neon, and then you've got these valence electrons. And finally, you can see all of row 4 has the same electron configuration as argon here, and then you have the valence electrons. And so, for example, lithium, instead of writing 1s2, 2s2, you can just replace this with this in square brackets. So lithium is just helium in square brackets, and then the valence electrons. Oxygen is, again, just the helium in square brackets, and then its valence electrons. Sodium here has the same electron configuration as neon, and then valence electrons. Phosphorus here has neon electron configuration, and then valence electrons. You're getting the idea. And it gets a lot quicker to do this as you go further down, obviously. It probably takes the same time to write HE as it does 1s2, to be honest. But down the bottom here, it's a lot quicker to write AR in square brackets than it is to write 1s2, 2s2, 2p6, 3s2, 3p6. Okay? And then vanadium with its valence electrons and its core argon electronic configuration. And that's selenium thrown into. Grab your periodic table and determine the electron configuration of these marked elements using abbreviated electron configurations. Press pause. Okay, A. A is 4s2, then 3d 1, 2, 3, 4, 5, 6, 7, 8, 3d8. And argon has the same complete electron configuration of argon, then 4s2 and 3d8, and that makes it nickel. B, we've got the electron configuration of neon, and then 3s2, 1, 2, 3, 4, 5, 3p5. So neon, and 3s2, 3p5, which makes it chlorine. Next, C, we've got the same electronic configuration as xenon. And then we've got 6s1, 6s2. Yeah, so xenon, square brackets, 6s2. And that would make it barium. And finally, we have the same electronic configuration as krypton, and then 5s2, 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 4d9 down here, and that would give us silver. However, what about, do they say, what about that? What do we need to do? That's right, one of these s electrons is going to skip into the d orbital, which would give us 5s1 and 4d10. An expanded form of the periodic table. It looks a bit different to the one you're accustomed to. You can see down the bottom there in the 6th period we've got barium, and then over there we've got lutetium. And have a look on a normal periodic table to see where these normally are. Okay, and also see if you can make out lanthanum 2 and where that normally is. Have a look. Okay, now in this expanded form, it's just written in order of atomic number as you go along. Okay, rather than the lanthanides being written down the bottom here and this being shifted along. Okay, and in this expanded form, we can see the order of the electrons would fill these sub-levels. Let's have a look. So starting here with the S block, it's 6s. Okay, 6s. Then it fills 4f, 5d, and 6p. So this is the order of filling. Here is a periodic table in Chinese. You will be given a test on this next. I joke, of course. You won't be getting a test on this, but it's very interesting. Look at it, really quite beautiful. Orbital box diagrams are another way of showing how electrons are arranged in an atom. They give more information about the distribution of electrons in the orbitals in a given sublevel. The electron configuration here tells us that it's 2 electrons in 1s, 2 electrons in 2s, and 3 electrons in 2p. The orbital box diagram tells us a similar thing in that it shows 2 electrons in 1s, 2 electrons in 2s, and 3 electrons in 2p. These arrows are representing electrons. However, it also tells us that in the p sublevels, electrons fill 1 each. They don't fill 2 by 2. The orbital box diagram has alternate styles. You sometimes see different types of arrows in a similar style, or you sometimes see the boxes drawn at different levels. Sometimes you just see them as lines with arrows through them at different levels, which you'll see on the next slide. And again, arrows represent electrons. Not the next slide, the slide after this one. Before that, we're going to look at Hund's rule and orbital box diagrams. Whenever electrons are placed in any given sublevel, each orbital must have 1 electron before electrons are paired. So you can see here with nitrogen in the 2p sublevel that each orbital has 1 electron. Okay, this is correct. Here in the 2p sublevel, you can see 1 orbital has 2 electrons and 1 has no electrons. So this would be incorrect. And you might be thinking, why is he drawing a photorealistic bus? Well, I'm producing this masterpiece to help you understand this using a metaphor. Much as strangers sitting on a bus will sit on 3 separate seats instead of strangers sitting next to each other and having a free seat, so electrons will choose to be alone rather than sitting together. So you can think of it as the strangers on a bus rule as well. Okay, here's some other types of orbital box diagrams. And sometimes you would see it. I'm just going to make my pen a bit bigger. Okay. Sometimes you would see it with them drawn with boxes like this too. Okay. You can see here that the orbital box diagrams may be drawn to show the relative energy of the different sublevels. So I've got 1s here, and that's at a lower energy. Then a 2s at a slightly higher energy level. And then you see the small difference in energy levels between 2s and 2p. This is for nitrogen. If I look at potassium, there's a lot more going on because there's more electrons. And again, you can see the ever increasing energy levels as you go from 1s through 2s to 2p, 3s, 3p and 4s. And I know what you're all thinking. Why do some arrows point up and some arrows point down? Well, the different arrows just show the spin of the electrons, and we don't need to worry about that. Okay. Goodbye.